Power series. Power series are now going to be infinite series, but they have an n and an x. Okay, so you can kind of think of x as a variable. This is in fact a way to define a function. We'll talk more about that thought process next week. For now, we're just going to look at it like this. What does this mean? C sub n x to the n. The general form, right? C0 plus C1x plus C0, whatever, right? So what that's actually going to look like, I'll put some examples down here. They're going to tell you what this formula is for n, and then there's going to be an x to the n. So the question for these is always going to be, for what x's does this thing converge? So the nice thing about power series, you don't have to worry about which test to use. You just always use the ratio test for each one. So you don't have to think about this or that or whatever. Well, as soon as you see that it's something with an x to the n, you're like, bang, I go ahead and then use the ratio test. We also have this one up here. This is the more general form. This is a power series centered at x equals 0. It's what you get if you put a equals 0 here. This is a power series centered at x equals a. All right. So in practice, for example, something like this. Let's look at one that we're going to be doing here later. How about this? Something like that. Okay? So rather than just being x to something, it's something in parentheses moved over. In any case, you will still be using the ratio test. So let's see how this works. All right, now let's start with these first 3 examples. And remember the question that we're asking here? For what x does this converge? And using the ratio test, so we're going to take the limit as n goes to infinity of an plus 1 over an. That's going to have some x's in it when we do the limit, right? Because x just will be going along for the ride when we take the limit as n goes to infinity. We need some expression here. And I'm going to make sure that it's less than 1. All right, but this might not always work very well. My first example is an example where it doesn't work real well. Often, by the way, the power series start from n equals 0. We take the, of course, we know x to the 0. That is going to be 1. We take 0 to 0, the factorial, 0 factorial, we previously in our lives, this is defined as 1. So if I actually write out what this is, it's going to be 1 plus x plus 2 factorial x squared plus 3 factorial x cubed plus 4 factorial x to 4. Okay, so we can expect some pretty bad behavior from this infinite series, right? Because those x's and those factorials drawing on this thing is pretty hopeless. But we can figure that out simply by doing the ratio test. Let's look at it. So if I have an plus 1 over a, I'm going to start back here. Run out of space so easily. Okay, this is going to be n plus 1 factorial x to the n plus 1. Whoops, forgot those. Divided by n factorial x to the n. All right, first of all, x here, we don't know what it is. X could be positive or negative. These guys, everything's positive. N, right, starts from 0. It's not going to be negative. But x could be values of negative. So here, I always, when I got a power series, I always have to use the absolute value. And what happens to it, it ends up going around my x. So this is going to be, I'm going to write this as this. I'm going to pull this x to the n plus 1. And then down here, I'm going to have n factorial, absolute value of x to the n. So these guys cancel. These guys cancel. But I still have n plus 1 absolute value of x. And so if I take the limit as n goes to infinity of n plus 1 absolute value of x, this is completely hopeless, right? This is going to go to infinity. Okay. For any value of x, except x equal 0. Okay. So basically, this thing diverges everywhere unless x equals 0. What happens if x equals 0? You have to worry about it here? I wouldn't. I would go back here. What happens if I put in x equals 0 here? I have 1 plus 0, 0, 0, 0, 0. Okay? So it will converge at x equals 0. But only for x equals 0. So the answer is this is very bad. Converges only if x equals 0. So for a power series, that's actually as bad as you can get. There's no way I can make that less than 1. So, another example, here's an example where we can work with this one a little bit better. Do the same thing. I look at the ratio test. So, 3 to the n plus 1, x to the n plus 1, over square root n plus 1, and then multiply by the reciprocal, root n, 3 to the n, x to the n. Again, everything is positive except possibly x. So, I'm going to move them around a little bit. And now I can get those. Okay, remember that x. And this is what should happen for your x terms, or x minus a, whichever one it is. What should happen is that the x to the n in the bottom is going to cancel the x to the n on the top, but you will be ending up with one absolute value of x. And whatever other garbage you happen to have. Right? So here we have this square root of n over n plus 1, and then we have 3 absolute value of x. Okay, so then what happens? Now I have to take the limit of this. Well, all right, you know what? I don't have a lot of space. So I'm going to, when I take the limit of this, I'm taking the limit as n goes to infinity. So the 3 and the root x don't do anything, right? This is what I'm taking the limit of. So I'm going to actually pull it outside when I rewrite it. I would have written this 2 steps, but not having a whole lot of space, and I'm going to erase. Okay. When I take the limit of this as n goes to infinity, I'm going to get 1. We know that. Okay. So this is 3 times the absolute value of x. Now for this to converge, I need this to be strictly less than 1. Okay? So what I'm going to do is make sure, now I have this thing. Right? So here. So what is that? So what I have is absolute value of x is less than 1/3, right? Or x is between negative 1/3 and 1/3. If I think about this on a number line, here's x equals 0. So here's negative 1/3 and here's 1/3. So this is where I'm converging. Okay? So in other words, I can call this has a name. This is called the radius of convergence. Now, we'll go back to this. And that's all I'm going to say right now. I do want to point out, I put 2 open circles here. I don't know if this one converges at 1/3 and negative 1/3 or not. That is another issue that we're going to talk about in the next lecture. Okay. In the next video. Right now, I just want to figure out sort of what that radius of convergence is. Now, for my last problem that was on the board before, looked similar to the previous one, but now instead of the n factorial being on the top, the n factorial is on the bottom. So this is much better, right? If I write this out, I can see, and you will become very familiar with this series. Okay, it looks like that. Okay? But what's going to happen here is very quickly you'll be able to see if I do my an plus 1 over an, this is x plus 1, wrong, x to the n plus 1 over, I don't know why I put these here, I'm just like, well, n plus 1 factorial. And then this is going to be n factorial over x to the n. Okay? So rewriting this, x to the n plus 1, n factorial over here. Underneath, I've got n plus 1 times n factorial and the x to the n. This guy goes, this guy goes. I have absolute value of x over n plus 1. When I take the limit of that, it's going to go to 0. Limit as n goes to infinity of this guy is equal to 0, which is less than 1 for all x. Okay? So this converges for all x. Okay? Any value, you'll have something that converges because this n factorial goes so fast. And now here's an interesting point. So what's the radius of convergence? In this case, we say the radius of convergence is infinity. Okay. So I chose these 3 examples, and in the first lecture so that you can see the three possible behaviors that we have. Okay, I'm going to write those up. So you have three possibilities. We have our power series, you know what? We're just going to do it around x equals 0. Because these are the three examples we have, right? All right, let me just write it this way. So you have one possibility, which is converges only when x equals 0. For this, we call the radius of convergence 0 because nothing there. Converges for some absolute value of x less than r, right? We'll call it r. Radius of convergence is r. In our example, it was 1/3. Third possibility, converges for all x, and in this case, radius of convergence is infinite. Right? Now, in my next video, we'll do a bunch of examples where it's not just around x equals 0, it's going to be around x equals a. But all this stuff just translates. So like when I drew this thing here, for my radius of convergence, it was x equals 0. In this case, it's just going to be something x equals a. Right? So the behavior is the same. Converges only at the center, which is x equals a. Again, we call the radius of convergence 0 there. What you're going to have, something is x minus a less than r. And then we're going to have radius of convergence as r. Third possibility is going to be converges for all x. And then our radius of convergence is infinity. I will do also an example or two where it's a little bit, sometimes instead of just being x minus 3 or something, it'll be like 2x minus 5. And then you have to mess around with it. I'll show you, because if it was like 2x minus 5, this a wouldn't be 5 because you have a 2 there, so like you have to factor it out. So we'll see that. We'll see that with an example. It's a little bit of pain, but it's no different. You still do the same thing. You still use the ratio test. So that's the important thing, right? In this last part of this video, I want to mention one more thing. It's all about the radius of convergence, but there's also something called the interval of convergence. Okay? The interval of convergence to find the interval of convergence, you have to check the endpoints as well. So let's go back to the problem one we had done. Here we go. We have this guy, right? And we have found here. So back up to my picture. This was x equals 0. This is 1/3, and this is negative 1/3. The issue with that is we don't know if those circles are open or closed, because those circles correspond to where this ratio was equal to 1. And the ratio test tells us nothing about that situation. So that's why if they ask you for the interval of convergence, you have to go back and also check the endpoints, right? So my endpoints are x equals 1/3 and x equals negative 1/3. I have to put both of those into my series and see what happens. At x equals 1/3, what do I get? 3 to the n, 1/3 to the n, root n. Well, these 3's cancel. That's just not doing anything. This is 1 over square root of n. So this diverges. Now what happens at the other one, though, I've got minus 1/3 to the n. So the 3's cancel, but I have a minus 1. Oh, it should be 0. No, it has to be 1. We have to start with 1, right? Dividing by 0. No dividing by 0, please. Okay, now look at this. This is an alternating series. And we did this alternating series. We showed that this converges by the alternating series test. Okay, so we showed that this diverges because of p series, p greater than 1, p less than 1. This one converges by the alternating series test because this 1 over n does the right thing. 1 over n. Alright, so when I look at my interval of convergence, when I'm up here in my picture, it's an open circle at 1/3, but it's a closed circle at negative 1/3. Or if I write down the interval of convergence for this problem in an interval notation, I have to include the negative 1/3, and I have to exclude the 1/3. Because it diverges at one endpoint and converges at the other. Now, the thing with these interval of convergence issues, it depends on what the coefficients are here in the formula. It might diverge at both endpoints, it might converge at both endpoints, it might converge at one and diverge at the other. So you have to check, if they ask you for the interval of convergence, you have to go through a lot more work and check that.